It's our pleasure to have Nisan Zuckerman today from Austin, who will tell us about hidden sets for RL.
Okay, thanks, Mark. Okay, so this work is motivated by the question of, is randomness useful in computing? So presumably most of you are familiar with this. We have lots of great randomized algorithms, but maybe there are corresponding deterministic algorithms that perform almost as well. So like for primality, the best algorithms are randomized, but right now we do know some deterministic algorithms that just lose a polynomial factor. So more generally, one can ask, does BPP equal P or does RP equal P? So BPP stands for two-sided error randomized polynomial time algorithms. On any input, the probability that you're correct is at least 2/3. And of course, you could amplify and get really high probability just by repeating it many times and taking majority. RP refers to one-sided error. So if X is in the language, then the probability that the algorithm accepts is at least 1/2. If X is not in the language, then the probability it accepts is 0. And again, you could improve the 1/2 to exponentially close to 1. So these are you can also look at these questions in the context of space. Do you need are randomized space-bounded algorithms any more powerful than deterministic space-bounded algorithms? So we know that. So of course, Savage showed that non-deterministic space is contained in deterministic space S squared. So for one-sided error, we immediately have that randomized space S is contained in deterministic space S squared. And it was also shown by maybe Borden, and it was shown some time ago that actually randomized space S is contained in deterministic space S squared. So up to polynomial factors, randomness and even non-determinism doesn't buy you anything. So really the question is, does randomized space S equal deterministic space S? And you can study this in either the two-sided error model or the one-sided error model. So these are major open questions. All of these, and they're quite difficult, but this may be more within reach than these, or should be. But and here it suffices if we actually do believe that these are equal. I think most people believe that at this point. So it would suffice to show that they're equal just for space log n, and that would imply it for any larger space, or space constructible. So if we restrict to log n, then we get the questions, does BPL equal L? That's BPL stands for BP space S. And does RL equal L? So these are the sort of guiding questions in this area. And we study this by modeling space-bounded computation as read-once branching programs. So we fix the actual input, and this is just looking at the random input. So in this model, we're using R random bits. So there are R layers, and it's a directed graph. So each layer represents a configuration of the Turing machine. So we're saying the width W is the number of nodes in a layer. So think of W as 2 to the S, or more or less. And so what happens in this program? There's some start configuration, and then the machine chugs along, and when it needs a random bit, it may, depending on the value of the random bit, it may move to one of these two configurations. So maybe in this case it flipped a 1 and it moves into this configuration. And then it goes along when it needs another random bit, maybe it moves into this configuration, etc. So this is the way that the randomized space-bounded machine computes. So as a mathematical problem, we're just going to restrict attention to such graphs. Of course, if there are any questions, feel free to ask. Please ask. So a very natural way to try to de-randomize algorithms is to construct pseudorandom generators. A pseudorandom generator is a deterministic algorithm that takes as input a small random seed and outputs a much longer string that's hopefully random enough for whatever purpose you have at hand. So in our context, we're interested in pseudorandom generators for read-once branching programs. So what we would want is one fixed generator such that for any with W read-once branching program P, the probability that P accepts the output of the generator is very close to the probability that P accepts a uniformly random R-bit string. These probabilities differ by at most epsilon. So if we had this would be a pseudorandom generator. So this is sort of our dream goal. And this is suitable for de-randomizing two-sided error randomized algorithms, BPL. A weaker object is a hitting set generator. A hitting set generator is more for de-randomizing one-sided error. So what is it? It says that for any with W read-once branching program P, if P accepts a uniformly random string with probability at least epsilon, then there's something in the hitting set generator that that's accepted. Okay, so probabilities aren't preserved, but just says as long as there's a significant probability in the random setting of P accepting, the hitting set generator will output one string x. X is the seed for the hitting set generator. There will be one output of the hitting set generator h of x that P accepts. And again, this is suitable for de-randomizing one-sided error, or RL. So in this talk, I'm going to discuss pseudorandom generators and hitting set generators for read-once branching programs. So I'll start out with the case of large R. This is R, again, is the number of random bits read. So this is the setting that we're most interested in. I'll give the history, the new result, and I'll give you the proof. And then I'll talk about more general R, and again, the history and the proof, and some bonus material. And concluding. Okay, so previous work. So first of all, again, our dream is a pseudorandom generator that matches the non-explicit bounds. So it's not hard to use the probabilistic method to show that there exists good pseudorandom generators. Well, I put pseudorandom generator in quote because a pseudorandom generator is efficiently computable. So these are not efficiently computable. It's non-explicit, but it fools all read-once branching programs. And the seed length is log of WR over epsilon. So and you should think of where W again is the width. So you should think of the parameters WR and 1 over epsilon as all being n. So the width is n, the length of the program is n, and epsilon is 1 over n. So Nisan, in that setting, this gives just log n bits for the non-explicit. Nisan showed that the seed length gave an explicit pseudorandom generator where the seed length is off from optimal by this log r factor. So it gives log squared n in this setting. So the whole sort of game here is, really we'd like to make this log squared n equal to log n. Impagliazzo, Nisan, and Wigderson gave a similar seed length in a more general setting. And actually, even for width 4 and constant epsilon, the best known is still log squared. This was actually, until recently, it was actually just W equal 3, but there was some nice progress on width 3. But there are more pseudorandom generators in restricted settings, so you can look at regular branching programs, permutation branching programs, so a variety of restricted models. But in this talk, we're focusing on the general model. So essentially, this was the best known in the general model until this very impressive work by Mark, Gill, and Sumega here at Princeton. And what they did was they constructed a hitting set generator with better seed length, at least as a function of epsilon. So the seed length is, right, so it has the same dependence on width and length as Nisan's, except now they have optimal dependence on the error epsilon. There's also one other issue, is that it's really O tilde, meaning there's some extra polylog factors here. So what's nice about this is now you can hit read once branching programs that have a very tiny success probability. Here if it accepts with probability n to the minus log n, you can still hit it using the same seed length, order log squared n, well, except for some polylog factors. Moreover, they actually constructed something even stronger called a pseudo-random pseudo-distribution, which I won't define, but this is actually suitable for de-randomizing BPL. So our new result is an improvement in many ways from this previous work. So we construct a hitting set generator with the same we remove the polylog factors from the construction of Mark, Gill, and Sumega. So now it's the same bound, except we just have a big O. So now we just need a seed of length order log squared n instead of O tilde of log squared n. Secondly, they start with a very elegant idea, but to make it all work, it gets very complicated and the paper runs to 60 plus pages. Our paper is 9 pages, including, the introduction and everything. So, I think it's fair to say it's simpler, and it's more general in ways that I'll tell you later. Except it's less general in that we don't construct a pseudo-random pseudo-distribution. So our work is only applicable to de-randomizing RL, not BPL. Okay, so our work, basically our proof proceeds by establishing a structural lemma and then exploiting it. So let me tell you the structural lemma first, then I'll tell you how we exploit it, and then I'll prove the structural lemma. So here's our read once branching program. The structural lemma is the following, that we can find some nodes V0, V1, V2, etc. We can find log n of these nodes such that the following holds. If the read once branching program accepts with probability epsilon, then the probability that we pass through all these nodes is similar to epsilon, say at least epsilon to the 4th. Moreover, it's pretty likely that you go from a VI to a VI plus 1. So it's at least 1 over n cubed, say. So I'm focusing right now on this general setting where the width and the length are n, and epsilon is n to the minus log n, so that we have these concrete.
So this lemma is only for this setting, or for any epsilon?
Right. It's for this setting. I'll state a more general lemma later that we need. We actually need a more general lemma for more general parameters.
What's the bottom probability exactly? Conditioned on being in VI, or?
Yeah, right. Yeah, sorry. Right. It's a probability starting in VI that you reach VI plus 1. Yeah. So we have significant probability of going from each VI to VI plus 1, and the probability of going through all of these is significant. Okay. So first, let's see how to exploit this. So the main idea is that the strings. Yeah, I should. Let's see. Okay. The main idea is that we're going to get a combinatorial rectangle just by looking at the paths from V0 to V1, V1 to V2, V2 to V3, etc. So let me elaborate on that. So again, we're going for seed length log squared n. So the first observation is, okay, we have these log n v's. We don't know which layer they're in, but we can cycle over all n to the log n possibilities for these vi's. The second idea is that to get from a vi to a vi plus 1, instead of using perfectly random bits, we can use Nisan pseudorandom generator with somewhat reasonable error. Just say half the 1 over 2n cubed between vi and vi plus 1. So this gives us seed length log squared n to go from vi to vi plus 1. So now the probability using Nisan pseudorandom generator that's starting in vi, we go to vi plus 1. It was 1 over n cubed. Now we lost this 1 over 2n cubed, but it's still at least 1 over 2n cubed. So that's still not too bad. So if we pick independent seeds using Nisan's pseudorandom generator between each vi and vi plus 1, we don't lose too much. The probability of going through all these vi's was epsilon to the 4th. Now maybe it's epsilon to the 5th. It's even a little better. Okay, so now we did that. Okay, so now again we've established this. Let's call that probability at least delta. Now the point is that the good seeds form a combinatorial rectangle. A combinatorial rectangle is just a cross product of sets. Okay, so this is very structured. We have a cross product of sets, G1 cross G2 cross GT, where each GI is a subset of 1 through 2 to the D. So it's a subset of the seeds. So each GI represents the good seeds that take you from VI to VI plus 1. So that's a subset of 2 to the D, and there are T of them. Okay, but now we can use, we've had hitting set generators for combinatorial rectangles for a while, so now we can just use them in this setting. So they're essentially optimal. These hitting set generators just use, if there are m dimensions, if there are t dimensions and each dimension has size m, and the probability and the density is at least delta, we get sets of polynomial in this quantity. Yeah, the log t may be surprising. We don't even need that, but we have very small sets. So we just substitute in this hitting set generator. So we just use this hitting set generator to pick the t tuples of seeds, and then we're done. And so that's it.
So it's not a PRG, it's just a hitting set.
Right, it's just a hitting set generator.
There's no PRG.
Right. So we don't construct PRGs. We only construct.
For this problem, there's no.
Oh, right. So right now the best known is loses some polylog factors.
So if you could use a PRG for this, you would get a PRG also.
No.
The structural lemma is not a PRG.
With the 4, and some probabilities change, right?
But the structural lemma it could be a weaker, something between a hitting set and a PRG.
Yeah, you could say that, but right, again, it's no good. Okay, there are a few problems, right? So one is that we're cycling over all possibilities for where the VIs are. So that's one issue, and then we lose something because of the structural lemma. But just to recap, okay, yeah, right. So for one such t-tuple, we do follow the path. So just to recap, what is the hitting set generator? I sort of gave a top-down view of it, but we let D be the seed length of Nisan's generator with this error. We let T be order log n for each of the n to the, and then we're going to try all possibilities for where the VIs are. So that corresponds to trying a bunch of ni's that sum to n, and we'll use the hitting set generator for combinatorial rectangles to generate seeds S1 through ST, where each SI is a seed for Nisan pseudorandom generator. And then we'll output this Nisan pseudorandom generator of S1 through ST. So this is just recapping what I just said. But that's it. Okay. So I still owe you a proof of the structural lemma.
So it's not a black box.
It's a black box.
It's black box.
It's a
cycling over all the path.
Well, we're just trying all possibilities. What do you? I mean, we don't look at the hitting right. The hitting set generator doesn't depend on the particular program. If that's what, right. We're just cycling over all possibilities. Yeah, to know which one works, we would need to know, but.
So the main thing is the structure.
Yeah, so the main, right, but you'll see that that's not too hard either. But let's prove the structural lemma. So again, this is the structural lemma. And so this follows inductively from the following. For any node U, there's another node V, such that the probability starting from U that we get to V is at least 1 over n cubed. And either V is the acceptance node, is the accepting node, or the probability that V leads to acceptance is much bigger than the probability that U leads to acceptance. So we let alpha be the probability that U leads to acceptance. The probability that V leads to acceptance should get multiplied by n, or let's say n over 2. I wrote n over 2, but you'll see why. Okay, if we know, so this says that, so if we do this inductively, we start from V0, we find a V1 whose acceptance probability is a factor of n more, and V2 is a factor of n more than that, etc. We started with acceptance probability n to the minus log n. After log n iterations, we'll get to an accepting node. Okay, and how are we going to prove this? So without loss of generality, assume that alpha is less than 2 over n. That alpha, again, is the acceptance probability from U. Because if it's at least 2 over n, we can just choose V to be the accept node. But then we know, right, then we'll reach the accept node with probability 2 over n, and it satisfies these conditions. So let's assume alpha is small. Okay, let's define a good node to be one whose acceptance probability is between an factor alpha n over 2 and alpha n. Okay, so really we want to hit one of these good nodes. We're looking for a good node. And notice that each accepting path from U hits a good node. The reason is that the acceptance probability can at most double. The out degree is 2. You have probability half of going on each edge. So the acceptance probability can at most double, because the acceptance probability from here is the average of the acceptance probabilities from here. Okay, so it's going to go. So if you reach probability 1, you have to pass through this interval of a factor of 2. Okay, let's call W unlikely if the probability of hitting W is less than 1 over n cubed. So really, we want to avoid unlikely nodes. Well, now we can just do a union bound argument. So the probability that we hit any unlikely good node and accept, well, there are most n squared nodes in our whole graph. It's unlikely if it means the probability of hitting it is strictly less than 1 over n cubed. And the probability of accepting from here is alpha n. So this gives us alpha. So notice this is why we need the upper bound here. Okay, well now we're basically done, because therefore there exists an accepting path hitting a likely good node. We said, right, the probability of accepting is alpha. Every accepting path passes through a good node.
So what was this? Why did you multiply by alpha n? So the probability.
Right, that's the upper bound here. So right, so we're looking at
Yeah.
right.
So it's among the good. Okay. Right. Okay.
Okay, so therefore they're right. So the probability of accepting is alpha. The probability of passing through an unlikely good node and accepting is less than alpha. So that means there has to be a path that hits a likely good node, and that's it.
So what is the epsilon is 1 over epsilon again?
Sorry, epsilon.
When do you use it?
Oh, yeah.
When do you use it? Epsilon, 1 over epsilon is epsilon again?
Oh, well, just yeah, this doesn't use it right. So it just when we apply, right, so this is sort of the structural lemma that gives us this is a sort of a smaller lemma that gives us the bigger lemma that I said before, and here's where we use that it's n over n to the minus log n, because we only have to repeat it log n times, because this right, but it would hold, but right, it would work even for smaller epsilon. It would give log epsilon over log n. Okay, so that's the whole proof of the hitting set generator.
So when you say you have to try all the different options for the VIs, you basically just have to try the different layers.
Right, different layers.
That's
Yeah.
the term. But could you use Nisan generator for the whole thing, and then just iterate with the product hitting set? Because is any restriction of the Nisan generator also somehow? So.
But we needed the independent. So I'm not sure of your suggestion. You want to use Nisan's generator and then what?
You can't use it. You have to really do Nisans on each different size block.
Right. We don't.
Because you need independence.
So you're wondering if just Nisan's generator will work by itself?
It's some combination of the hitting set for block for products.
I mean, certainly instead of Nisan's generator for each thing, we could do a big Nisan's generator and just restrict to this. But we would have to use independent seeds or.
By the way, you could have reused it, but you need a better epsilon. You could have reused this one.
We could have used.
It's not entirely obvious. But you need a better. You have to set a smaller epsilon.
Okay, I'm not sure. Okay, we could discuss it later, maybe. Any other questions? Okay, so that's really the. Okay, so now let me tell you about for small values of r. So here we'll change the problem. Before we had our real program and we wanted to know the smallest seed. Now I'll tell you we only want to use a seed of order log w bits, and the question is how long a program can we fool? Okay, so of course non-explicitly we can take the length of the program to be polynomial in the width. This is the setting, the original setting that we were just looking at. Actually, there we had c equal to 1. Trivial, we can certainly, if the program just has length order log w, we could use the identity pseudo-random generator and it would fool that. So this is trivial. So the first people to improve this were Itai-Komlosh and Semeretti, who gave a hitting set generator when r is close to log squared w. And here they got epsilon, which is 1 over poly in w. Okay, so they improved it a little bit, but we're trying to get all the way to w to the c. Nisan and I gave a pseudo-random generator for any polylog w, so log to the cw for any c. But our error wasn't as good. It was 1 over w to the little o of 1. Right, so it doesn't strictly dominate this. It's better in 2 ways, that it's a pseudo-random generator and that it's longer output, but it's worse in the error. And Armoni, well, it's not exactly. He just showed how to interpolate between our generator and Nisan's original generator. Okay, so our new results are basically we can give a hitting set generator for any polylog W, and this time with optimal error and optimal seed length. So it's the first strict improvement of AKS because NZ didn't strictly improve it. So it's a better error than NZ, but NZ is a pseudo-random generator, so so it's not completely better. We also give a hitting set generator making analogous improvements to Armoni's generator, but again, Armoni has a pseudo-random generator. We just have a hitting set. So our seed length really is this quantity. Let me try to parse this. So right, so this is sort of what you'd get from Nisan with even constant error, log WR times log R. We're going to divide by something and add, and we have an optimal dependence on the error. And the thing that we divide by is log W minus log R, if it's at least 1. So in other words, if the width is much bigger than the length, then we can divide by something and get a savings. So that's the bound. I mean the exact parameters. And so here we're going to here we have to modify the structural lemma. So here the structural lemma says for any node V there exists, instead of one node W, we get a whole set S depending on V in some subsequent layer, but some fixed layer, such that the probability that you go from V to SV is significant. And SV is either the acceptance node or for every node in this layer SV, the probability that you accept is significantly larger. Okay, so instead of finding one node where we increase the success probability, we find a whole bunch of nodes where the success probability has increased. And we say with good probability we hit that whole set. Okay, and the proof of this is similar, so I won't go through it. And and now we have to modify the hitting set generator in this general setting. So we won't be using combinatorial rectangles. We don't have a combinatorial rectangle anymore because it goes from a node to a set, and we lose the combinatorial rectangle. But we can still do something. So we use a suitable based pseudorandom generator, which in the general setting we'll use Armoni's generator, or you could say, right? So we'll use Armoni's generator, and we'll use something called a hitter, which is just a disperser to move from one good set to the next. So I'll tell you what. I'll just define that in a second. So hitter. I'll write it down. Here's the definition. So it has two inputs and one output. And the idea is that if we have any set of outputs that has some density, say theta, then the probability that if we choose the first what's the word? Okay, the first part of the input randomly, the probability that there exists something in the second input that hits it is very high. So it's a way of amplifying. It's a way of amplifying the success probability. I'll give you a picture here. This may be easier to follow. Right. So now I've drawn it as a graph. So the hitter takes two inputs. The first input we'll write on the left. The second input we'll think of just choosing an edge here. And it outputs a set of strings D, in 0, 1 to the D. It says if we start with any set here that has density at least theta, right? The probability that there exists Y that hits this set should be very large. So in other words, this X is a bad choice because all of its neighbors failed to hit this. This is a good choice because it has a neighbor that hits it. And we're saying that the only ones that fail, there aren't too many that fail, just a beta fraction fail. So if you're familiar with dispersers, you'll recognize that this is really just a disperser in disguise. Not that much disguise, really. Okay, so now what's our general hitting set generator? So we start with a hitter, and this is the property. So we pick a random x in 0, 1 to the L, and the idea is that the intuition is that if we start with a random x, if we cycle over y, we should, with good probability, we'll find one that the base pseudorandom generator moves us from V to some set in SV. So we'll be able to, so the whole idea is to move from V to SV with good probability. And now we can cycle over y prime. We can find one such that once we get to this W, we can find something that the base pseudorandom generator takes us from W to some node in SW. Okay, so we keep on doing this, and it should work. The probability of failure, there are at most W times R nodes altogether. Right? W is the width, R is the length. There's WR nodes in the whole graph, and each of these has failure probability at most beta.
The problem is that the SVs are not in the same layer.
Right, the different SVs are right.
No, each set SV is in one layer.
Right, each SV is in one layer, but it's not. But you could start with V's in the same layer, and the later SVs may be in different layers. But so that's why we do the union bound over the whole thing. It may be avoidable, but I don't know.
And here you enumerate over the SVs, because before you enumerated over the VIs.
Right, so really, right, as Zev mentioned, I should have said really we're enumerating over layers. So we just have to enumerate. We have to enumerate over layers again.
Okay, but in each layer you have to decide where is this SV? Or?
Not for the generator, no. No, because right, as long as we pick the right layer, everything will take care of itself. We'll just move from V to SV, and then once we get a good node there, we'll move.
So that was before also, so I missed that. Okay, so you didn't have to know before which are the VIs.
Right, we don't have to. Yeah, right, just the layers. Yeah, I should have said the layers. So, right, so just recapping here, now our generator looks like this, right? So we start with a base generator, and now we have, right? So now we have to cycle over all choices of the lengths, but not the SVs, just the lengths, and the output of the hitting set generator is just the base generator from X to Y1, base generator from here, where the ith output has length Ni. Okay, so it's just a recapping of what we just said. Okay, so now let me tell you a couple of applications. How much time do I have? What time am I supposed to have?
20 minutes.
20 minutes. Okay, so yeah, I have plenty of time. Okay. So let me tell you about de-randomizing small success RL. So of course, hitting set generators and pseudorandom generators are key tools to de-randomizing randomized algorithms, but there are actually some more clever de-randomizations. In fact, a famous one, Sachs and Zhu, showed that actually RL, in fact BPL, is contained in deterministic space log to the 3/2 n. So just using Nisan's generator by itself would give you log squared n. But they gave a clever algorithm that actually does better, log to the 3/2 n. So they don't construct a new pseudorandom generator to do this. They just managed to do the de-randomization. Another extreme example, which is much older, is Savage's theorem that says that RL, in fact NL, is contained in deterministic space log squared n. So we can use, so we have a new theorem that interpolates between these two. Our new theorem says that now now imagine an RL algorithm with success probability epsilon. This can be simulated by a deterministic space algorithm using space log to the 3/2 n plus log n log 1 over epsilon. So in particular, NL corresponds to epsilon, which is, say, 1 over 2 to the n. So if epsilon is 1 over 2 to the n, after 1 log we get n, after 2 logs we get log n. So we get log squared n, and we recover Savage's theorem from here. And if epsilon is large, then this last term is small relative to the first term, and we recover Sachs-Jou. I mean, we actually use these two in our proof, so it's not like, but it's a way to interpolate.
You use this black box, or you use the techniques?
We use it as a black box. Yeah, I'll show you the proof. The proof is, yeah, from what we've said, it's not hard. So let me tell you the proof. The idea is we're not going to use our pseudorandom generator, just the structural lemma. So we use the Sachs-Jou algorithm to compute a directed graph where we put an edge uv if the probability of going from u to v is at least 1 over w cubed. And there's no edge if the right, and we ensure that there's no edge if the probability is 0. Okay, so we can do this using Sachs-Jou, and this uses space log to the 3/2 n. And once the main point is that by our structural lemma, if p accepts, then there exists a path from start to accept of length at most log 1 over epsilon. In fact, log 1 over epsilon over log n. So the idea is just to run Savage's algorithm on this graph. And if you remember Savage's algorithm, more generally, right, the paths are of length log 1 over epsilon, so we have this recursive halving. So we can do it in space log 1 over epsilon times log n. And then and that's it. So right, this part took space log to the 3/2 n, and this took space, this. So that's it.
Do you get anything because NL is closer than the complement? Do you get anything from the by inductive counting?
I see. So you want to. So you're wondering about BPL or something, or
No.
Just
the intersection of the
just like some. Yep. So yeah, I haven't thought about anything there. So
we're already placing into some space class, which is obviously closed under complement.
Oh yeah, right. This is closed under. Yeah. Okay, we also have a way to simulate randomness in NL. So here the theorem is that if we have an RL algorithm for some language L using R random bits, then there's actually an NL algorithm for L using fewer bits, R over polylog n non-deterministic bits. So in some sense, here we're saying sort of each non-deterministic bit can count as polylog random bits. And this isn't too hard either. The idea is to replace blocks of length polylog by the output of our hitting set generator. But I won't go through the proof, but it's not hard. Okay, so in conclusion, we gave a new simple hitting set generator for small success RL with optimal seed dependence on epsilon, which matches the best known hitting set generators and other parameters. And so can we, of course, it would be great to have a pseudo-random generator with similar seed length. That would be great. Maybe somewhat easier would be to construct a pseudo-random pseudo-distribution, which is what Mark, Gil, and Sumega did. But they lost these polylog-log factors. Can we avoid losing them? Can we give maybe we can look at restricted models. So Mark and others had nice pseudorandom generators for regular read-once branching programs? Can we design better hitting set generators?
Actually, we have a hitting set with the optimal seed length.
Oh, you have?
for
Oh,
regular, yeah. It's in the same paper in the journal version.
oh, okay. All right. I missed. Okay, well, good. Okay, so. And finally, does an optimal hitting set generator for RL also imply that BPL equals L? So this might seem crazy to ask, but actually it's true in the polynomial time setting. An optimal hitting set generator for RP does imply that BPP equals P. Okay, and yeah, that's it.